A few things to say. First, there's no quiz tonight because we just have a lot of things going on. And second, the people who haven't taken the lab test yet have the lab test tonight. It's really fast. People seem to start leaving after about 25 minutes, and the whole class seems to be gone before an hour. So it's fast, but painful. Like getting hit by a bus. Not really. I don't know. Maybe it is. Yeah, that's true. It's a slightly worse analogy, yeah. And the second thing, this is the weird thing. Okay, so we have the exam on Monday, exam 3. Well, that's not 10 anymore. Oh yeah, it's Halloween. Yeah, right. We talked about that. I'm told that we talked about it. So here's the weird thing. Like, this is stupid. I have not had this happen before in my 8 years here, but I moved some topics around because I thought it made more sense, and like I'm always fiddling with stuff. But then the way they matched up with the problems, we have not. This class would be okay, but the day class hasn't gotten far enough to do the new set of problems. And so the topics for this exam are exactly the same as the topics for last exam. Okay, so that's dumb, but that's how it is. But anyways, so you have a chance to look back over stuff and maybe solidify some stuff, you know. Just remember to go back over, you know, it's cumulative, so go back over the old stuff.
If we do worse than the last one, can we keep the last score?
You get to keep them both. But it seems like that would be sensible, but no. What?
Will we have time to go over the last example since we're ahead?
Oh, yeah, we could. Yeah, sure, we could do that.
So none of the new stuff is going to be on there?
Right, none of the force stuff. So it's still just up through two-dimensional kinematics.
Will we make up the quiz from tonight?
No. The other ones are just going to pick up the slack for it. So all the quizzes will still add up to 20%, but just divided over one less quiz. Yeah, still. Yeah, exactly.
So kinematics of particles into these not on it?
That's
Kinetics?
no kinetics. Right, no kinetics. So no mass or force. Yeah. There's 5. Yeah. So yeah, I mean, there's going to be extra topics on the next one. So you should, you know, if you have time. I mean, I know studying for the test is your top priority probably, but if you have time, you should start getting to the kinetics problems, because right, there's going to be extra topics on the next test. That's the downside of all this. Yes.
Which problems can you do?
You can do any of the. You can do all the free body diagram problems. No, that's not true. And you can do anything in free body diagrams or Newton's second law that doesn't involve friction. So if the problem says friction, then skip it. But everything else.
Which would be like 90% of the...
What, have friction? Let's look. I don't trust. You could have doctored it. Okay, so free body diagrams. Oh. You can do, are these the right free body diagrams questions?
You can
Okay.
do A, but you can't do B.
Oh yeah, you can't do B. You can do all of 2. You can do 3. You can't do 4. You're right, there is a lot of friction on those. Maybe we'll get to it today.
If it says friction is second.
And then Newton's second law. You can do 1 and 2. You can do 3, 4, 5, 6. Ooh, you can do almost all the Newton's second law ones. You can't do 8 or 9. You could do 9A if you were a little brown noser. So you could do 9A, 10A if you wanted. Okay, so there's a few there you can get started with. If you do more than that, I'll be surprised. So start working on free body diagram problems and Newton's second law. So should we go through the test or just selected problems on the test? Oh, yeah, sure. Do that first. You have it? Yeah. All right, so let me do this example, and then we'll talk about questions you have on the test. So this is the example from last time. You have a 1 kilogram cart in contact with a 2 kilogram cart. And there's a 10 Newton force pushing, so this is 1. The bigger one is 2. 10 Newtons pushing on the left, and 5 Newtons pushing on the right. And we want to find the acceleration vector. And second, we want to find the force on the 1 kilogram by the 2 kilogram. You could write that as the force vector on 1 by 2. All right, so if we're trying to calculate the acceleration, what do we want to isolate? It's basically always the same. Yeah, isolate the whole thing. So there's weight. It has a mass of 3 kilograms, so the weight is 3 times 9.81, so 29.43. And then there's an upward force. I'll call it N total. You also could do it as N1 on one side and N2 on the other side. But we'll just lump it all into one force, N total. And then the only other So now mentally go around the boundary and look for contact with the outside world. There's a 5 Newton force acting here and a 10 Newton force acting here. And now Newton's second law says that 10 Newton force is in the positive x direction, so 10, 0. The n total is in the positive y direction, so 0, positive n total. The weight's in the negative y direction, so 0, negative 29.43. And the 5 Newton is in the negative x direction, so that's negative 5, 0. And all that's equal to the mass times the acceleration. The mass of our chosen object is 3. And what do we know about the acceleration? Yep, it's only horizontal, so I'm going to write it as a0. And what if it turned out to be in the negative x direction? Would I have to do that? Would I have to recognize that at the start? No, because this answer can come out being negative, and then when you plug a negative answer back into that vector, you'd get the vector pointing the right way. So we can just always write it as a0, and which direction along the x-axis it is will work out in the math. So the x component says 10 minus 5 is equal to 3a. And so a is equal to 5/3. So that's 1.6 repeating. And then the y equation isn't going to end up being useful for what we're asked to find, but you could use that to figure out that, so n total minus 29.43 is equal to 0. So n total is equal to 29.43. We want to calculate the acceleration vector, so we want to take that variable value for a and plug it back into this, which is the acceleration vector. And so the acceleration vector is equal to 1.6 repeating in the x direction, 0 in the y direction, meters per second squared. So what direction does that vector point? In the positive x. I was hoping I could make more people like do that disco move. You were like the only one. Wait, show me again and again. Okay, so 1.6 repeating like that. Those are two equivalent, equally good ways of representing a vector. And then the second thing, any questions about that part? Second thing we're trying to find is the force vector on 1 by 2. So all things being equal, you might as well isolate the one that you're trying to find the force on, because when you choose a body to isolate, all the forces that you draw are going to be on that body. So sometimes you can't do that, and then you have to use Newton's third law, but which isn't really a problem. But so for part B, we're going to isolate the 1 kilogram. That's what I said, right? On 1. Okay, so there's the 1 kilogram cart. There's a weight force of 1 times 9.81. There's the pushing contact from the floor. That's not the same one that we had before, because the one we had before was the pushing contact on both 1 and 2. So this is just the one on 1, so I'll just write it N1. And then there's a pushing contact on the right side. That comes from the 2 kilogram. So that goes this direction, and I'll call that R. And then the last thing is the pushing force over here of 10 newtons. Any questions about that free body diagram? So now Newton's second law says, well, the 10 Newton force is in the positive x direction, so 10, 0. The weight force is in the negative y direction, so 0, negative 9.81. N1 is in the positive y direction, 0, N1. And R is in the negative x direction, so negative R, 0. And all that is equal to the mass of the chosen body times the acceleration. And now we know the acceleration is 1.6 repeating 0. So the x equation says 10 minus r is equal to 1.6 repeating. I'll subtract 1.6 from both sides and add r to both sides. So we have 10 minus 1.6 repeating is equal to r. So r is equal to 8.3 repeating. And you can see from this that we already have everything we want. We could use the y equation if there was anything we wanted to solve for, but we might as well just skip it here. Okay, so we have this variable r, but the problem asked for the force vector applied to the 1 by the 2. And that's what this is, the force on 1 by 2. So now we have to take this positive value of r and plug it back into this vector. It's going to make that component negative. So F on 1 by 2 is equal to negative 8.3 repeating 0 newtons. Or, what direction is that? Show me a couple times in case I forget. Oh! Okay, so 8.3 repeating that way. The 5 did not show up because it's applied to the 2 kilogram cart. And so we just apply the weight, and then we go around the boundary of whatever we chose, and any stuff that isn't happening to the boundary of what we chose doesn't show up. Okay? So that can be a confusing thing, but you can keep from making that mistake if you just keep reminding yourself, all I'm doing is going around the boundary and looking for things touching the boundary. Okay, so can anyone think of a way to check this? Like, say it was really important to get this right. It was for work or whatever. How could we check this? What? Well, yeah, that's right. So I'm going to do it again, alternatively. But this time I'm going to isolate the cart 2. We're going to calculate the force on 2 by 1. And then we're going to use Newton's third law to figure out the force on 1 by 2. So I'm going to draw a free body diagram of the 2 kilogram cart. So the force is acting on the 2. There's a weight of 2 times 9.81, so 19.62. There's the normal force from the ground. I'll call that N2. There's the 5 Newton force acting over here. And then on the other side, there's a pushing contact from cart 1. I'll write that as R. It is going to have the same value as R, but the idea when I'm doing this, I'm sort of pretending that we haven't already done it the other way. We're not going to use any of the information that we just came up with. We're going to do it separately and hope that those answers come out the same. If they don't, we made a mistake somewhere. Okay, so Newton's second law. That R is in the positive x direction. N2 is in the positive y direction. $19.62 is in the negative y direction. And 5 is in the negative x direction. And those are all equal to the mass of 2 times the acceleration that we calculated in part A. So 1.6 repeating 0. So the x equation says R minus 5 is equal to 2 times 1.6 repeating, which is 3.3 repeating. And so add 5 to both sides, and you get that R is equal to 8.3 newtons. And again, the y equation doesn't give us anything we're looking for particularly. Okay, so now we need to interpret this force R. We're looking for the force on 1 by 2. That's what we were asked for in this problem. This force here, what's that? Force on 2 by 1. And so the force on 2 by 1 is equal to 8.3 repeating 0. And you could also think of that as a vector with a magnitude of 8.3 repeating in the positive x direction. And so the force on 1 by 2 is equal to this same magnitude force, just in the opposite direction. And what's that in components? Yeah, negative 8.3 repeating 0. So does that match what we got in the other way? Yeah. Which is, I don't know, isn't it great? It's sort of, I mean, it's surprising, I think. I don't know. It always is cool to me that you can, so we did it this one way where we have the 10 Newton force. We did this other way where we don't, but we have the 5 Newton force. Everything still works out, you know. It's cool how that works. the reason it works is because of the accelerations in both of them telling them what's going on that we're not told about. Okay, I want to say one thing about Newton's third law, too. Notice that one other way to think about Newton's third law is this. Like another way to state, another statement of Newton's third law. That's Newton's third law, because I like acronyms. Says the force on A by B. Can you, so on A by B is equal to negative force vector on B by A. So if you calculate the vector components for like the force on something by something else, and you want to figure out the components of the force vector on the something else by the original thing, just switch the signs of the components. So if the force on A by B is 2, 1, the force on B by A is negative 2, negative 1. Yeah, that's plenty. Any questions about any of that problem? Okay, so let's take a minute and is there anything about the test anybody has any questions about? What? Do 3? Yeah. Okay, so an object is launched horizontally from a height of 20 meters. 20. There's a bug on yours. Oh. Okay, so it's launched horizontally. It follows a path like that. That's okay. So it starts out horizontally. And the first thing we want to figure out, and we know the height is 20 meters. And so part A says, how long until it hits the ground? First, we have to choose those 4 things. So time equals 0, time final, the origin location, and the coordinate system. Time equals 0 is when it's launched. Time final is when it hits the ground, or really technically the instant before it hits the ground. And the origin and the coordinate system, I'll put oriented like this on the ground beneath the launch point. So those two are shown. Okay, so now we'll list out what we know, what we want. Do we know how long it takes to hit the ground? No, that's what we're looking for. Do we know the acceleration? Yes, it's because it's free fall. So AX is 0. AY is negative 9.81. Do we know the initial position vector? Yeah, PIX is 0. PIY is positive 20. Do we know the initial velocity? We know something about it. We know that it's like this, and we don't know what the magnitude is. Like you could represent it like this for now. We don't know how fast it's going, but we know that it's totally moving in the x direction. And so VIX, we don't know. But VIY is equal to 0. If you have a velocity that's horizontal, the y component is 0. And then, yes. Well, it's not just velocity, actually. Any vector that's in the direction of, entirely in the direction of one of the axes, or negative of one of the axes, has a 0 component for the other one. There's no angle, but it says horizontal. And so from horizontal, you could draw the picture like this. And then one way you could think of it is if you put the, then the angle is 0 degrees, so you'd have like your speed times cosine and sine is 0. Sine of 0 is 0, so. And then we don't have to know anything about the final velocity for this, so I'll just leave that out. Although deep down, what do we know about the final velocity? We know that, well, we still don't know anything because we don't know but the x component of the final velocity is always the same as the x component of the initial velocity. That's because there's no acceleration in the x direction, so there's nothing to change that component of the velocity. But we always pretend we don't know that because it actually simplifies using the equations. All right, so what equation can we use with this? I think we should be able to use PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. Oh, and I skipped the PFs. We know something about PF too. We know that when it hits the ground, which is what it's doing at time final, the y component of the position is 0 because our origin is on the ground. So 0 is equal to 20 plus 0 times TF, that's just 0, minus 4.905 TF squared. And I think if you solve that for TF, I remember you get something like 2.02. You get, when you take the square root, you get plus or minus 2.02. This is a time, so we only use positive values. So that's it for part A. Any questions about that? And And then for part B, now we're going to imagine that the horizontal distance it travels before it hits the ground is also 20 meters. Is there any reason to change any of those four things that we have to choose? Nope. So we can just go right back to this, and whatever we knew before, we still know. And now we also know time final, and we also know PFX because now it's given. So let's see, TF is 2.02. We know AX and AY still. We know PIX and PIY. We know PFX and PFY. We know VIY is equal to 0. But we don't know VIX, and that's what we're trying to find. We're trying to figure out how fast it has to be moving in the X direction to land 20 meters away horizontally. And so I think, again, the equation that works is PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So 20 is equal to 0 plus VIX times 2.02 plus 0. And I think if you calculate VIX, you get something like 9.90 meters per second. Any questions about that one? Any other problems you'd like me to do? Are we going to do that thing where we go, I do 4 and then I do 1 and then I ask if anyone wants to see another one and there's like a long pause, but we all know what's going to happen? So a ball is thrown from a height of 2 meters at a speed of 30 meters per second. The angle's given. Let me just draw this picture. So it's something like this. It starts at a height of 2 meters, and it starts, that starting velocity is 5 degrees above the horizontal, so this is 5 degrees. And the magnitude of that velocity at the start is 30 meters per second. And we want to figure out horizontally how far away it is when it hits the ground. Okay, so I have to choose these. Time equals 0 is when it's thrown. Time final is when it hits the ground or right before it hits the ground. And then the coordinate system, I'm going to do the same thing I pretty much always do. Just put it on the ground beneath the object's location at time equals 0. The y-axis up, x-axis in the direction of motion. Do we know time final? No. Acceleration, it's free fall, so we know that. Do we know P initial? Yep, PIX is 0. PIY is positive 2. Do we know anything about P final? What do we know? Yeah, we know PFY is 0, and we're trying to find PFX. We can get that initial velocity from the speed and the angle. So if we put the tail of that vector at the origin, the angle we're using here for the initial velocity, that's not 30 degrees, that's 30 meters per second. Okay, so the velocity vector is 30 times cosine of 5 degrees, 30 times sine of 5 degrees, and that's 29 point something, 89, and then like 2.6, I think. 2.60? 1. So VIX is 29.89, and VIY is 2.61. And we'll leave out V final. All right, is there any equation we can use to find PFX? No. So we need TF. And TF we can find using this equation. PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So 0 is equal to 2 plus 2.61 TF minus 4.905 TF squared. And you can solve this with the quadratic formula, so that's A, that's B, and that's C. And if you solve the quadratic formula, you get something negative. We know we don't want that. And you get like 0.95, I think. And so now we can plug that back into this equation. PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So Pfx is equal to 0 plus 29.89 times 0.95 plus 0, and you get 68 point something, 60, right? 60 something. Oh, that was really far off. 28.6 meters. Any questions about that? Okay. Let's skip 1 and 2. If you have questions about those, ask me after class or something. Okay. Back to kinetics. So now there's a type of problem that we're going to see a lot of, and that's where an object is rolling or sliding along a surface that isn't horizontal. We've already done some problems where things are rolling or sliding along surfaces that are horizontal. So this is a trick that's always helpful for problems involving sliding or rolling. Along non-horizontal surfaces. So for example, let's say we have a cart rolling along an incline like this. Where this angle is 15 degrees. And there's a force applied, let's call that 250 newtons. And what we're going to do is, so here's the trick. Always choose the y-axis pointing out of the surface. And then the x-axis has to be horizontal. Not horizontal. The x-axis has to be like parallel along the surface. So the y-axis points out of the surface like that. And then the x-axis is whatever it has to be for this to be an acceptable coordinate system. Okay, so what's the benefit of this? Because it better be a good benefit, because it seems kind of like a wacky thing to do. All right, well, let's think about these things force by force. And also let's think about the acceleration. So the forces that we have, there's a weight force, there's a normal force, There's the 250 Newton force. And then the last thing we care about is the acceleration vector. Let me draw a free body diagram of this just to, so we can see all those forces. We won't see the acceleration, but so there's a weight like this. I'll just write that mg. And there's a force normal, perpendicular to the surface. I'll call that N. That's a pushing contact from the ground. And then there's the 250 Newton force there. Okay. So let's start with, I have all these listed out. Let's start with that normal force. I'll come back to the weight in a second. What would that normal force vector look like if we had our standard coordinate system? Well, that normal force is not, that's right. And so it would be, it would be n times cosine and sine of 15. In other words, it would be like an ugly vector. The math, it's not like it's impossibly hard, but it's messy. Like always in the past, that normal force has just had one non-zero component and one zero component. Now it would have a cosine and a sine, so it would appear in both equations. But with this rotated coordinate system, what direction does n point? Just in the positive y direction. So the normal is always in the positive y direction. And so it's just always going to be 0n. You never have to think about it. And whenever you can eliminate thinking, that's better. What about that 250 Newton force? What would that look like with a standard coordinate system? 250 times cosine and sine of 15, because it's at an angle with, okay? So again, that one would have x and y components. Messy. But the 250, well, that doesn't appear in every problem, but things like it appear most of the time in these. This is in the positive x direction. Now the normal force. No, we already did that. The acceleration. What would the acceleration vector look like in the non-rotated coordinate system? Well, we know that all it can do is move along here, right? So we could represent it as a variable a times cosine and sine of 15 degrees. But again, that's messy. We have a variable appearing now in both of those two equations. This system of equations is just getting uglier each time that happens, But in the rotated coordinate system, what's the acceleration? Yeah. I'll say it always has a 0 y component. And so we can always just represent it as A0. Okay, so that's 3 good benefits. I can't wait to see what it does to help with the weight force, because that was already simple. So now imagine how simple it's going to be now. So that's the trade-off, is that, well, in the non-rotated coordinate system, the weight force is nice and simple. It's just in the negative y direction, Now it's ugly. Okay, so this one got uglier. Now this is going to be the weight times the cosine of, if you think about that angle, well, yeah, let's think about it. So it's like that. Our coordinate system is like this. And this angle here is 15 degrees. One way to think about that is we know that this angle is 15 degrees. And so if you think of this whole green coordinate system as starting in its usual orientation, okay? And now you tip it up 15 degrees to make the x-axis align with the surface. As you tip it up, you're tipping the negative y-axis over the same amount away from the negative. Can you see what I'm talking about? And so this is, the weight force is mg times the cosine of, in this case, 270 minus 15. This is 255. And mg times the sine of 255. Negative 1, it would be negative,
So not 150, 105.
yes.
Did you just do negative 15?
No, because the signs would be wrong. So the key thing is that as you tip this coordinate system, you're tipping the negative y-axis away from the weight. In the standard coordinate system, the negative y-axis and the weight are aligned. Okay? So now, however much you have to tip this to make it line up with the surface, that's how much you're tipping the negative y-axis away from the weight force. And so you're always adding or subtracting that angle from 270. But we'll get a lot of practice with that. Okay, so we're going to do this because we got 3 benefits and only 1 drawback. So overall, it pays off to do this. But we switched from the weight always being the easiest thing to represent in vector form to the weight being the only thing that's complicated to represent in the vector form. Okay? So let's say we have an incline at 45 degrees. And a cart on the incline. The cart has a mass of 50 kilograms. And let's say there's 100, just a 100 Newton force pushing up the incline. And we want to calculate the acceleration vector. The coordinate system we're going to choose has the y-axis out of the surface. And so in order for this to be an acceptable coordinate system, does the x-axis have to point up or down the incline? Down. And so I'll draw a Freebody diagram. Notice that the steps for doing this problem are exactly the same as the steps we've been using. The only difference is that now we have to we have to make sure that our vectors are right in this sort of unusual to us coordinate system. So the free body diagram, there's the cart. There's a weight force of 50 times 9.81. That's 490.5. There's a pushing contact from the ground. I'll call that N. And there's a 100 Newton force parallel to the surface. And you know you're done with the forces because we've gone all the way around the boundary and there's nowhere else that the outside world touches the boundary. Okay, so now Newton's second law. Well, n is always the same. That's just 0n in this rotated coordinate system. No matter what way the incline is working, we always have the y-axis pointing out of the surface. So this is always, these are always the components for the normal force. And then what are the components for the 100 Newton force? Yeah, that's in the negative x direction. So that's negative 100, 0. And then we have to calculate the weight. So the weight has a magnitude of 490.5. Let me move it over. And the coordinate system is like this. There's the x-axis. There's the y-axis. The incline makes an angle of 45 degrees with the horizontal. That means that the weight force makes an angle of 45 degrees with the negative y-axis. So we know that this is 45. And now we just have to think, does this picture tell us that we're adding 45 to 270? 270 is the negative y-axis. So are we adding 45 to 270, or are we subtracting 45 from 270? We're adding in this case, because going counterclockwise from the x-axis, you go through the negative y-axis and keep going to get to the vector. So this is, so theta is equal to 315 degrees. And so if you calculate that, you get positive 346.84, negative 346.84. So now that, that ugly thing is the weight force. It would have been simple if we would have kept the same coordinate system, but now it's messy. But we have all these other benefits that outweigh that one. And then that's equal to the mass of the chosen body, 50, times the acceleration vector that's always the same. We represent that as A0. That A could come out positive or negative, but we'll just let the math do that. And so the x equation says negative 100 plus 346.84 is equal to 50a. And so if you solve that, you get that a is equal to positive 4.9368. I don't know why I chose so many significant figures. But. And then the acceleration vector is this, so you can plug that value back in. And you get 4.93680. Meters per second squared. Okay, there's another way you can write that. That's with the components. The other way is to show the direction and the magnitude. Be careful with this one, because we're used to thinking of this as something with a positive x direction as being straight to the right, horizontal. But now our positive x direction points down at an angle. So this vector means that the acceleration is this, with a magnitude of 4.9368.
Because that you drew the 100 pointing like up.
Yep.
Doesn't mean that it's going up.
Right. So what happens is you can see that's a pretty steep incline. Gravity, if you didn't apply any other forces, gravity would make this accelerate downwards pretty fast. And so that 100 just isn't enough force to keep it from falling down. It's pushing to try to hold it up, but it's not pushing hard enough. Any questions about that one? Let's stop there. So